Darcy's Law and Fluid Flow Rate of Porous Media by Sarah Beltran. Introduction. Studying flow rate is something that is common and required for math majors like myself to learn about in courses like differential equations, calculus 3, and vector analysis. It is an important application that is used and studied by engineers and architects to build structures to the best of their capabilities by knowing the fluid dynamics and the fluid mechanics behind it. In order for me to test Darcy's Law and its reliability is to construct a homemade aquifer and test the fluid flow rate after filling the aquifer with different porous materials and comparing it to the estimated fluid flow rate that I would obtain by plugging my numbers into Darcy's equation. Darcy's equation is given by Q equals Ka in parentheses H1 minus H2 over L, where Q is the estimated flow rate, K is the porosity of the media in proportion of pore space, and A is the cross-sectional area of the cylindrical container used in centimeters cubed. H1 is your water inlet height in centimeters, and H2 is your water outlet height in centimeters. Materials and methodology. The materials used in this experiment include a homemade aquifer composed of a 2-liter bottle, molding clay, aquarium tubing, and a sharp knife. Aquarium sand was also used, as well as aquarium gravel and bentonite clay, which was in the form of cat litter. A beaker and a food scale were also used, and a stopwatch was used to record the flow rate. A funnel was used to ensure from spillage, and water was used. First, we must assemble our homemade aquifer. After this is done, we weigh our porous media while it is dry, and we measure the desired volume of water we wish to pour into the bottle. We then measure the flow rate with a stopwatch. Once the fluid has stopped draining, we stop recording time. We then weigh the wet media in order to obtain the final volume of the water and the volume of the media. We continue to do this for 10 trials with sand, clay, and gravel. We use a z-test to determine whether or not we get the same mean flow rate for the observed and the expected. The first thing we must do is calculate the constant K, which represents the porosity of the media being used, and it's calculated by finding 1 minus the bulk density over the particle density. I did these calculations myself and found the average porosity of sand to be 0.36. Gravel turned out to be 0.232. Clay had a result of 0.192. As you can see on this table, we have an average flow rate of 0.576 for the sand and an average rate of 0 for clay. The water never passed through. And we also have an average rate of 7.74 milliliters per second for gravel. Z-tests were performed in order to detect whether or not the expected flow rate from Darcy's Law coincided with the observed flow rate in this experiment. The results are shown on the right. As you can see, the z-test showed for sand a z-score of negative 6.5155 with a p-value of less than 0.0001, which showed to be extremely significant. We also calculated the z-score of gravel. We got negative 3.2995, which had a p-value of 0.001, which also showed a significant difference. As you can see, whenever I did my experiment, the clay did not yield the water. We had a flow rate of 0, which ended up making our z-score a negative 31,264 with a p-value of less than 0.001, which showed a significant difference. As you can see from the graph, none of the error bars overlap, which proves there is a significant difference in the means of the expected and the observed fluid flow rates. Darcy's law implicates that the less porous the media in the container is, the slower it will flow. This experiment has demonstrated otherwise and is shown to be inconclusive, as z-tests have shown that all of our observed flow rates are significantly different than our expected flow rate. Therefore, we must reject our null hypothesis. More tests will need to be performed in order to draw a more valid conclusion.